Okay, now we move on to this chapter, third chapter called Climate Change Through the Ages. And of course, we learned in the previous sections. I have this is the 10th section of this course, and I have covered some of these topics from other places, but this book, What is Climate Change by Gail Herman, can stand on its own. So I'm going to include some of the material that is a repetition of something elsewhere, but if you only stick to this section 10, then you can learn everything except that there are some details which are missing in this book. Chapter 11 or section 11 covers another book which has more information that is missing here, so you can complement these things together as you want. Okay, so what are we learning here? We are going to look at hot house, ice house, snowball, just in terms of words. These three terms have all described Earth in the past. Hot house means when dinosaurs were running around, there was no Arctic ice, there was no glaciers on Greenland or the mountains like Himalaya or Antarctica and so on. And obviously sea level would have been much higher, but then you also had continents slightly different because continental configurations kept changing through time, and they're still kind of changing, but not evident in short time scales. Ice house is when you had glaciers, as we already talked about in the past as well. We've talked about glaciers and how they form and how they leave evidence of past climate. And there are snowball Earth episodes which I have mentioned elsewhere as well, which means the freezing came very close to the equator. There was snow and slush all the way down to the equator. Now you imagine continents like Asia and Africa and South America all covered in snow and ice, even the ocean covered in a lot of sea ice and so on. So these terms have all described Earth in the past. Also means that the temperatures have varied a lot, right? And what do we have to worry about then if global warming is happening? Well, these things happen when we were not around, so it's not so much about whether planet will disappear, but planet can have hot houses, ice houses, and snowball Earth episodes and so on, but we are not used to them, so we may not survive these things. So at times, over the course of billions of years, which is a lot of years, the planet has been a hot house with much warmer temperatures than we have now. It's been too warm for any glacier or ice sheets to form. At other times, Earth has been an ice house, cold enough to create much larger glaciers and vaster ice sheets. Planet has even been a snowball Earth, covered almost completely with ice, slush, and snow. Remember that life was already there in the ocean, so if you cover the entire ocean with ice, light cannot get through depending on how thick the ice is, and then without light, photosynthesis cannot go on in the ocean, and other living beings that depend on the photosynthesized carbohydrates and sugars like we do from plants and so on cannot survive. So we need slush Earth, maybe snow cover or slushy ice in the low latitudes for light to get through and sustain life in the ocean and so on. That's just kind of the detail, but obviously Earth has had a very exciting past, and all of them are forced by natural variability, which means we were not around to increase the greenhouse gases and change the energy balance. It was because of the changes in Earth's orbit around the Sun. Earth's orbit is elliptical. The Earth is tilted to the orbital plane at 23.5 degrees right now, and it precesses at some time scale. So the ellipticity can change, the obliquity can change, the precession produces time scales. So there are many time scales from 26,000 to 41,000 to 100,000 year changes, What is the most important thing? We learned about systems. So when you make a small change in the energy distribution or the energy coming from the sun, then internal feedbacks can begin to amplify the small change in energy, which we call the vicious cycle or positive feedbacks. And the best one you already know is, of course, the ice albedo feedback. If you begin to melt the ice or glaciers, then albedo goes down and you absorb more energy, it gets warmer, more glaciers melt, more albedo decrease, more energy kept in the system, and so on, and it can run away and become lots of glaciers can disappear very quickly. Why is that important? Because that's what is happening now. You're increasing greenhouse gases, warming the temperatures, melting the glaciers, reducing the albedo, and ice albedo feedback is already happening. Arctic is seeing some of it as the warmest region right now, the fastest warming region, and so on. So all these feedbacks are there in the system, whether they are kicked off by the changes in sun's energy or orbit of the earth, or they are changed by our input into greenhouse gases, they will still act. So we have to be careful. How do we know all these things happen? So we have to learn about the past climates, and we use scientists like me or my colleagues and friends use different methods to figure out what the climate on Earth was like hundreds and thousands and even millions of years ago. It's a nice detective work that includes all kinds of evidences that are there in the Earth system. We examine things like tree rings, the growth bands that develop within tree trunks. The rings are wider in warm years and thinner in cold years. So as the tree begins to grow, each year there is a ring as it gets fatter and fatter, and you can see here that you can drill through and look at the rings. It started in the center here and it kept growing and growing, and you can see how old the tree is by counting the rings. And sometimes the rings are closer like here, and sometimes they are farther apart. So when it's warm, the rings are wider so it can grow thicker. Typically temperatures favor growth and faster growth, and thinner in cold years. So even in the tropics the trees grow less when it's colder than normal, and grow faster and grow more when the temperatures are warmer than normal, and so on. There are also many other evidences. We look at coral reefs that are millions of years old. Reefs have growth bands, plus they hold a form of oxygen that helps measure long ago ocean temperatures. That sounds very complicated. Maybe I'll add a few words here. Coral reefs are basically it's a coral polyp. It's an animal that builds a structure out of calcium carbonate like this, and it invites all the other symbiotic algae to come and sit on its infrastructure, its building, and photosynthesize, so that CO2 produced by the coral is taken up by photosynthesis and oxygen is produced. And once you have photosynthesis, you get little zooplankton. So phytoplankton photosynthesize, zooplankton eat the phytoplankton, little fish eat the zooplankton, bigger fish eat the smaller fish, and so on. And soon you have like a rainforest in the ocean, nice symbiotic relation with lots of fish, and coral is happily living. But as it grows, it accumulates calcium carbonate, and calcium carbonate has oxygen, and that oxygen, you are used to thinking oxygen atom is atomic number of 8, and oxygen molecule is 16, 8 protons plus 8 neutrons. But you know that isotopes can have more neutrons. As long as the nucleus has 8 protons, it will be oxygen. Right? 6 is carbon, 7 is nitrogen. But naturally in the world there are some oxygen atoms that have 10 neutrons, so you end up with something called O18. O18 is obviously heavier than O16, and you have essentially processes that begin to affect begin to be affected by the weight. For example, when evaporation happens, you probably already know that water molecule is being taken out of the ocean into the atmosphere, so the lighter water molecule jumps out first. So O16 jumps out first. So H2O will be H2O16. Less of the H2O18 will jump out because it's heavier. And when it rains from the atmosphere, more of the O18 will fall first because it's heavier, and O16 remains. So it's a very nice, fascinating story which tells you, by looking at the O16 and O18 in the corals, in the ice, in the glaciers, in the ocean, sediments and so on, you can say how temperatures in the past have changed. Okay? They analyze ancient shells buried deep in the ocean that contain the same form of oxygen as the corals do. So we always have tracking ability of O16, O18, and we can say whether the temperature was cooler than now, warmer than now, and more glaciers were there before than now, or less, and so on and so forth. We also drill deep into the glacial cores to get samples of ancient ice. Tiny air bubbles trapped inside tell us about CO2 levels and temperatures. We have already talked about this in other sections, and in the first chapter, Things Are Heating Up, we talked about glaciers, how they form and what their properties are, and how they are different from regular ice. If you freeze the water and form the ice like sea ice, you get brittle ice. But when you keep dropping snow on land or on mountains, and you keep dropping more snow on top, it gets compressed and becomes a glacier, and the glacier flows down the hill like molasses or honey. So it has behavior that's very different than frozen water like sea ice. So to form glacier, you need to be on land, because snow falls, doesn't melt, more snow falls on top, as we said before, and it keeps getting compressed and becomes frozen ice-like, but it's glacier because it has different properties than ice, and so on. So we have lots of very interesting stories from the past about when the plants evolved, when we had jellyfish-like things, and then came the insects, the flowers, the seeds, and the pollinators, and the birds, and the dinosaurs, and then the mammals dominated. So there have been incidences, meteorite crash happened, and things just got explosive in terms of the amount of water vapor. The meteorite crash would have thrown up the dust, and maybe wildfires and diseases started, and the dinosaurs couldn't live through all that. They went extinct. Then some other species takes its space and begins to grow rapidly, and mammals did that after the dinosaurs went extinct. And we think that birds came out of the dinosaurs as well over time, developing feathers and learning to fly, and so mutations happened, and so on and so forth. So we'll come back and see that the story is an old one, and the climate always changes. But as you know by now, climate always changes because there are always changes in the orbit, or continents, or volcanoes, and so on and so forth. But now we are the agents of change. We are taking out carbon buried in the earth. We are burning it rapidly and increasing carbon dioxide and other greenhouse gases like methane and nitrous oxide, and causing a trapping of the thermal energy that wants to go out to balance the sun's energy coming in. And this is warming the temperatures, melting the glaciers, raising sea levels, increasing water vapor, making rainfall, extreme cyclones, and sea level rise, etc., etc., etc. Right? So I'll come back and continue that discussion in the next podcast. Okay? See you in the next podcast.